Well, shall we begin? I'm going to talk about the history of computers, the hardware aspect. Next time, the software, and finally, the applications. Computing probably began in ancient caveman days when they dropped some pebbles in a spot and put some more in and caused addition by adding of pebbles. Probably something like that was the beginning of counting. Now, it was very early necessary to be able to count fair-sized numbers. When somebody in the tribe came rushing into the chief and said, "I saw a herd of deer out there, we got to go out and kill them," the question of how many? Because if there are only 3 of them, you don't send the whole tribe out, but if there's a lot, you do. So very early, much as you may not think so, cavemen faced the problem of how big numbers really are. You will find all kinds of things written by ethnologists talking primitive tribes who are supposed to only know 1, 2, 3, and many or something, but it's pretty clear they did know more. Now, a guy named Marshack from Harvard in the museum was looking at old bones from caveman days and noticed that these bones were scratched in a regular fashion. The dents had a shape as if they were scraped one by one, and they occurred pretty much connected with the phases of the moon. Now, you living as you do, don't think much about the phases of the moon, so I'll take you back to something I read about Jane Austen's time. Jane Austen, remember, was around the time of Napoleonic Wars. The book observed they gave parties around the time of the full of the moon. In the dark of the moon, they didn't have enough light to get around very well. They didn't want to run a carriage with the weak lamps through dark nights and muddy roads. They were restricted to roughly a period about every lunar month. They had another bunch of parties. It's only recently that we could ignore the phases of the moon and get on with living independent of it. So primitive societies were very dependent upon that. Stonehenge, which you may remember, is that lovely stone erection on the plains of Salisbury in England. The first period was 19 to 1700 while they built one. Then 17 to 15 and 15 to 14, all of them BC, were periods when the thing was built and rebuilt and rebuilt. It's pretty clear that it's got something to do with astronomy. There are some stones which line up very well for the equinoxes and the solstices. And we have buildings from India, China, and Mexico which are called observatories because they look like they were used for observatory, but we're not always sure just how they were used. And on the plains of our country, there are big stone circles which are clearly being used for coping with astronomy. Astronomy implies a fair amount of computing. So there was a lot back there. Even if you don't have written records, they probably were doing things like that. Now, a sampan and an abacus were a couple of devices, you probably know the abacus better, for doing computing. They're little simple devices. They're fairly effective. But the coming of the Arabic numerals from India to Europe through the Arabics, but Europe adopted a different form of the numbers that the Arabs used, was a tremendous effect. I sometimes tell my friends the reason why Rome fell was Caesar put on a 3% sales tax, and there wasn't time to do anything else calculating Roman numerals. Try it yourself someday. Think how hard it is to calculate Roman numerals. Why they had to have an abacus. The coming of the Arabic numbers was a tremendous effect, but it was opposed. Up to 1400, there were laws passed saying you may not use these newfangled Arabic numbers, particularly that number 0, which has no meaning. After all, there was no such thing in the Roman numeral system. And the idea that a symbol stands for nothing caused great mental agony. Still, the practicality won out in the 1400s. It was too useful for the dynamic business society not to use Roman numerals to keep their records. And so it came in spite of opposition all over the place. Now, the next big one is the invention of logarithms by Napier, 1550 to 1617. He was a Scotch laird, fairly knowledgeable guy, And he invented logarithms, although it's kind of confusing. His are not the natural logarithms you learned in the calculus, but they're another funny brand. A guy from London College went up Briggs and persuaded him he really wanted to build logs of base 10, which is the one you're familiar with. You work in log 10, although all calculus took place in the base E. Now, out of that came a slide rule, which you probably haven't seen. Slide rule was a device for calculating, and the lengths on the slide rule are logarithms. And this is the standard one every engineer had. He wore it on his belt, and you knew an engineer because he had it. And if he didn't have a slide rule, in another case, he wasn't an engineer. And there's a famous story. If you want to see the length here, and if I want to multiply 2 by 3, I set the number at 2. That length is logarithm. I add the length of log of 3, and I get 5.99. If I'm very good, I get 5.995. It was a standard joke about engineers not being able to multiply 2 times 3 and get 6. But the people who repeatedly told that joke were people who had not mastered the slide rule. Now, the standard slide rule was like this. It was a complicated thing. This is a log-log deci trig, meaning it's got logarithm scales, meaning I can calculate a to the b power. The deci trig means that I've got the decimal versions of angles. I'm not in degrees, minutes, and seconds, but I'm in degrees and decimal parts of degrees, and I've got the sine and tangent, other useful things there. And I've got a folded scale, so I want to multiply by pi or divide by 5. I shift the scale I'm reading, and such nice things. It was standard. Every engineer had one. They no longer make them. The coming of hand calculators wrecked them. There just is no market for them except for museums, except a few people like me who could use them still. Well, Napier also devised Napier's bones, which I'll talk about in a few minutes. The slide rule like that is a standard one. There was at Bell Labs at one time about a 20-inch one, a round center part, instead of a sliding stick, a whole round part and a bunch of scales and a magnifying glass. You could get 4 and 4.5 figures out of it if you really worked hard. But that was a very elaborate thing, and I only saw one of them. I didn't really use it. I only played with it for a while to see how it worked and determine, yes, it is that good, but not much better. Now, the next thing along the same line of analog computing was the differential analyzer. Kelvin's brother, the family name was Thompson, invented an integrator. And from that, nothing much happened for a long while until Vannevar Bush at MIT around 1930 devised an integrator which was a rotating glass disc and a little small wheel on a lead screw. The further out you went, the bigger the function was, the smaller and it was less. And the rotation of this was the d theta, that was the f of theta, d theta. And you could integrate. And that gave rise to the MIT differential analyzer number 1, which is a big, massive iron thing with rods and connection rods and plotting boards and so on. And copies were made at Pennsylvania and so on, and one at Aberdeen. And later on, there was the RDA number 2, which the connections, instead of being by gears, were through a patchboard of electronics. And the integrators were very nice mechanical devices still. And I used that machine in 46 and 7, or maybe 47 8, to calculate the early trajectories of the Nike missile. And on it, I found out that instead of launching slantwise, you want to go up and come down in a ballistic path and come down from above. You will have more maneuverability with wings about 1/3 as big. So the machines were very useful. But it's no longer in existence. It was a very good machine, all things considered. During World War II, electronic computers were developed, particularly by Bell Labs at Whippany, gun directors. But you couldn't have a mechanical wheel and disc like that out at sea or in the field, so they did integration by electronics. They charged a condenser. The intensity of the current was f of t, and dt was the time elapsed, which means you could only integrate with respect to time. Now, these gun directors were very nifty, as I told you the other day. They were well debugged, well seasoned by temperature compensation for the Arctic and the tropics, and In fact, they had antifungal stuff on them so the tropics wouldn't get too much fungus and so on. And we had one, couple M9 gun directors condemned one time lying around, and so we took all the parts and brought them out to a common telephone patch board, all with a 1 meg ohm impedance, and we had a general purpose analyzer. We just connected it any way we wanted. And it was so popular that I finally had a second one made to connect with the first one or to run independently. So we had analog computers, and they've done good work. I don't want to minimize how important analog computers are. They are useful, but they're not terribly interesting mentally. They are very limited, they are very, very troublesome to use, and they have limited accuracy. 4 or at best, you cannot get 5 places out of an analog computer. And you frequently want 8 and 10 places nowadays. So they don't fit in too well except the low accuracy problems. Now returning to digital ones, I said Napier devised some bones which are simply some ivory rods which you could, with moderate charity, multiply one number by another. You pick the rods with the multiplicand on them and lay them up next to each other, and you read off the thing and you got the products you wanted very easily. Well, that led to Babbage, Schickert. Schickert lived in December 20th, 1623. He wrote a letter to Kepler. Kepler is the astronomer, and he says, "I'm sorry, but we had a fire and the machine I was building you burned up." Well, from pictures and other things we have, the thing has been reconstructed. And you can see the machine would roughly add, subtract, and with some charity, multiply and divide. The same year that letter was sent, Pascal was born. You often read Pascal built the first computers, but here was one built earlier, which would multiply and divide. And Pascal's would only add and subtract because his father was a tax collector and only had to add numbers. Our boy Leibniz of calculus fame put in multiplication by a very simple trick. You have a gear of potentially 10 teeth. If you want to multiply by 8, you cut off 2 of them, and you rotate, you advance the other one by 8 places. If you want 6, you cut off the first 4, and you rotate it by the other. So that by gears having some teeth taken off, you could multiply by that factor. But he didn't get them to work reliably. And that's one thing you have to have. Now, Babbage is the next one, 1791 to 1871. Babbage was minor nobility. He had the idea of building a machine because he had been using tables, and the tables had errors. And he said, if only a steam engine would make them, they would be accurate. So he set out to do it. Now, his first idea was a difference table. You probably know that if I take a polynomial degree n and differentiate, I get one lower degree. If I differentiate, I get another one, until I come down to a constant. Same way, if I take differences, if I take a polynomial degree n and take the first differences, they will be a polynomial degree n minus 1, so on. So the k differences of a polynomial degree k will be a constant. And I can build up by addition the original formula. Therefore, locally, any function which is approximated by a polynomial, I can, by the simple process of repeated additions, tabulate the function. And Babbage wanted to print out the numbers so there was no possibility of human error. Well, the technology to do this was beyond his abilities. He greatly improved manufacturing and engineering techniques of building this and that, but he never got it done in spite of government supports. Schutz and his son in Sweden did, in fact, build a couple different analyzers, and one of them was in Albany, New York, at the astronomy observatory there. It was used to build tables for quite a few years. So it really worked. But Babbage never completed it because what happened to him is what happened to a great many people. He no longer was well into one, and he had the realization of a better machine. In fact, he had the idea of a general purpose computer. Why bother this difference machine which could only do simple things when I can build a general purpose computer? So he started doing that again with government money, and again he did not complete it. It was not his fault, probably, although he was a bit irascible. Perhaps with a better temperament he might have got it done, but probably not. The technology was not equal to it. However, somewhere in the 1990s, the British, at a museum where some of the parts were, completed the design using not heavy gears made out of brass, but plastic gears, and the machine ran just as Babbage had designed it. It was, to a great extent, a von Neumann type machine. It has storage, it has a mill, which we call the arithmetic unit, it had a store, which is typically called memory, it had all the features, and it had branching. And Lady Lovelace, also known as Ada, for which you get the name Ada language, was a friend, and she wrote some programs for calculating, if the machine were ever built, things like the Bernoulli numbers and so on. And she had a pretty good grasp of what computers could and couldn't do. But as the machine was never completed, it died. And was pretty well lost until we built quite a few machines and found out we were already anticipated 50 years or more before, in fact, almost 100. Now, the next practical one was a Comptometer, which is a curious little machine. It was rectangular. The keys, you pushed them down. When you released them, the spring pulled them up at a fixed rate. And if you pushed a 9 down, it advanced the thing 9 times, a 7 to 7, and so on. And if you wanted to take 46 and multiply it by 12, you put your fingers, hit the 4 to 6, hit it twice, shift over 1, hit it once, and you had 12 times 46. And so what you did is you put your fingers to form, hit that many digits, moved over, hit that many, and you got a multiplication. And the essential feature was it didn't matter how hard you hit it, it was the release that did the addition. So they could get control and be accurate. And I saw many of those. They're very widely used. And of course, the division can be done by going the other way. And if you went negative, the machine rang a bell, and you went too far to back up. Now, from that machine came the more modern billionaire Frieden, Marshack, and Monroe, of which computing was widely based upon. At Los Alamos, besides the IBM computing machine we had a set upstairs with desk calculators, there probably were 50 or more desk calculators running around, which would add, subtract, multiply, divide. The earliest ones you cranked, but pretty soon you pushed a button to add, the button down, and the thing would turn as many times as you added. And gradually they mechanized until actually you punched the divide button and the machine would do dividing, throwing the carriage over and everything else for you. And indeed, one machine could do square roots, all by gears and levers, not by electronics, although they powered them with electric motors. At Bell Labs, when I went there in '46, there were 4 groups running desk calculators, almost always ladies. Men were not eligible for such a job, so there was discrimination against men. The math department had a smaller group. The network department had a much bigger one. The switching boys had one, and the quality control had a very large one because Western Electric was very concerned with quality control, and there was a great deal of quality control work because you may remember that quality control by Schuhart was a Bell Lab employee who got involved in this during the First World War and the Second World War, trying to produce reliable stuff. Now, punch cards came in because somebody in the Bureau of Census observed regarding the 1880 census that was taking a lot of time. And the 1890 census would take more than 10 years, and they would have to start the 1900. The Constitution says a census every 10 years. And they saw they were falling behind, and the hand methods they were using would not cope. So he persuaded somebody named Hollerith to do something about it, mechanize it. And Hollerith started mechanizing it by building sorters and Hollerith cards with round holes in it, which IBM finally converted to rectangular holes. They built tabulators and other things and gradually polished it up, but he finally left, and all of them ended up with a company which was IBM. Another guy there, Powers, ended up with Powers organization instead. And the difference was that Powers stuck with the round holes where fingers felt, and the rectangular ones, which came in, about 1928. Because they were using electric sensing, and so when I went by, they wanted to brush to get a constant one, so a rectangular hole was better than a round hole. About 1935, IBM built a multiplying punch. After all, your rate of pay times the number of hours is how much you're going to be paid. You've got to do some multiplication. So that got in, and they built about 1,500 of those on rent. Now, the difference between a machine on rent and a machine built and bought is a machine built and bought may not be used, although it's owned. Thus, when I was at University of Illinois as a graduate student and a biology friend of mine asked me if I could do a problem, there was a harmonic analyzer in a glass case just waiting for it. So I scrounged around and found out where to get the key to unlock the case and do various other things. I ran the problem, got the answers for them nicely, and I left it in a form with the certain thing displayed on the graphical part and the pen in a certain place. Approximately 10 years later, I was back, and I went on my way to look. No one had touched it since I had. The machine was there, but it was not being used. It had not been used before me. It hadn't been used afterwards. Whereas IBM, when I tell you there's 1,500 on rent, you can be sure they're being used or the guys will quit paying the rent. The 601 multiplying punch was the basis at Los Alamos for our computing, except we had a couple of machines, two of them, which would divide or do a triple product, A times B times C. They were special things which were very valuable and speed up things a bit. But fundamentally, a 601 was the backbone of the calculation. And it did about an operation per second. Now, in the mechanical, meaning really relay, Stibitz, George Stibitz, who just died about a week or so ago, I read his obituary, in '39 built a complex number computer. He had realized that you could do computing with relays. And as a test, because network theory requires multiplication, addition, subtraction, complex numbers, he built a complex computer. Would work. You sat down, typed in the complex numbers, you could add, subtract, multiply, and divide. It was a couple relay racks in a broom closet on West Street. And about a year or so later, it was exhibited up at Dartmouth with a terminal in Dartmouth and the computer down in New York. So you had a remote terminal running it. Furthermore, in the West Street building where it was, there were 3 terminals. You flicked a switch, you got the orange light, somebody else had it. You flicked the switch on and you got the green light, it was yours. And so there you had multi-terminal computer back in early 40s. Now he went on and built a bunch more, and a bunch came out of those. Samuels, then a guy named Andrews helped, and I got involved in Model 5s and Model 6s. About the same time, our boy Aitken was building machines at Harvard. And there was a guy in Germany, which we knew nothing about, named Zeus, who was building relay machines and partially electronic machines in Germany. He had much more trouble. He got bombed out here, there, and yon, and he had trouble with active war. I've met them all. I know Stibitz moderately well. I knew Aitken somewhat better, and I met Zeus several times. I'm inclined to believe of the 3 of them, Zeus was by far the greatest person and the greatest man in computing, considering particularly the trouble he had and the fact that he not only contributed to the hardware, he was one of the few hardware people who made any contribution to the software. Partly because there was nothing else he could do. His machine was hiding in Switzerland, half wrecked, and there was no hope of doing any building machines, so he turned to using machines. And he was a very bright guy and a very impressive person. I met him several times at Los Alamos, and I'm very impressed with his abilities. Now let me see if I can get you some idea of what these things mean. I told you hand calculators. I had a bevy of girls doing it. They could do about 1 operation for 20 seconds. Now you're going to say, I can do faster. You can for short times, for a day or 2. But week in and week out, answering the telephone, going to the John, doing other things, 1 operation for 20 seconds is about what you're going to get out of a lady running a desk calculator, or a guy too, it doesn't matter. Yes, you can get 2 or 3 times as much under duress, but for a practical job, 1 operation for 20 seconds is reasonable. The relay machines I've been talking about did 1 operation in about 1 second. Some were 1.5, some were a little bit less, but they were running roughly 1. Magnetic drum machines were maybe 1,000 operations if you stuck fixed point, but if you wanted floating point, which is necessary for scientific work, you were down around 15 since you had to simulate floating point. The IBM 701 type did about 1,000 operations a second. Current ones, about 1990, do around 10 to the 9th for a single processor. It's the fastest of the von Neumann types. We got a little faster than those. Now I've got, well, let's go on. I had it in the text to introduce the words milli, 10 to the minus 3, micro, 10 to the minus 6, nano, 10 to the minus 9th, pico, 10 to the minus 12, femto, 10 to the minus 15, and atto, 10 to the minus 18th. We don't have very many 10 to the minus 18th seconds. We have kilo for 10 to the 3rd, mega for 10 to the 6th, giga for 10 to the 9th, and tera for 10 to the 12th. And as far as I know, I've not filled in the two bigger ones than that. But you do hear of memories, terabit memories, 10 to 12 bits. Now let's get those down to human dimensions so you can understand the numbers. In 1 year, they're about pi times 10 to the 7th seconds. And in 100 years, your lifetime, they're 10 to the 9th. If you did one multiplication per second, all your life, day and night, 24 hours a day, a modern machine with 10 to the 9th multiplications would do the job in 3 seconds and probably get them all right. That is what has happened. That's what is the difference between a modern machine and you. You just cannot do what modern machines are, and take some time to understand it. Now another way to approach it is that the velocity of light is 3 times 10 to the 10th meters per second, roughly, a little bit less. And in a nanosecond, 10 to the minus 9th, light goes in a vacuum about 1 foot. In a picosecond, it's going to be about 1/100th of an inch. If I've got picosecond pulse rates, I've got 1/100th of an inch between pulses. And you can see why on an integrated chip, I must have the parts close together if I want to operate fast. Otherwise, all the time is going, get the pulse from here to there. I have to have it all close. Now, to get it another way, what is the natural dimension of nature? Well, atoms typically come around 1 to 3 angstrom. An angstrom is 10 to the minus 8 centimeters. That comes out of optics. Angstrom 10 to the minus 8, 1 to 3 angstroms. And in the crystals, they're typically around 10 angstroms apart. In a femtosecond, light can go across about 300 atoms at best. Now, if you think of a transistor as being germanium with some impurities, if I built you a transistor with 1 impure atom, you're not likely to believe it would be reliable. If I put in 1,000 atoms of impurities and lower the temperature down to, say, liquid air so the background noise is down, you might say, well, you know, Hamming, you might be able to build one like that, which means I've got something like 10 to the 9th atoms in the damn thing. It's about 1,000 atoms on the side. I'm not going to get much smaller than that. God made the atoms the way He did, and we're stuck with what He did. Therefore, I've got to have things close, even at atomic size. Now, the velocity of light being what it is, things I told you a moment ago can't go very far. You can't signal usefully very far in short times. The third thing is heat dissipation. There have been talks about thermodynamic machines which will reverse themselves, absorb all the heat back and so on, and publish a lot of papers, but I've seen nothing and I believe nothing about it. It isn't likely to happen in my lifetime, although it's not an impossibility. So when I make more and more components in a smaller and smaller place, I'm generating more heat. And when I make it more changes of state per unit of time, I'm producing more heat. So I have a really terrible problem of getting the heat off one of those little chips. And we are now looking at the fact that diamond is a very, very nifty heat conductor. Can we lay a coated diamond down, or some other compounds that are very much like diamond? Can we put that down at the bottom to get the heat out and conduct it out? And I think you will find that we will do that gradually. Heat is a real problem and it's not going to go away, I don't think, in your lifetime, but maybe. Now, to speed up machines, we've gone to 2 to 4 and sometimes more. But you see, if I have two arithmetic units in it, I can't compute twice as fast. I told you interference, crosstalk, and so on. If you have 4 of them, about the best you can hope is 3 times the speed of 1. If you go to 8, you can hope something maybe like 5, but you aren't going to get that very often, except on carefully chosen problems. You can't get your money back, so it is not a very good way to take a von Neumann type machine and put several processors in there and try to get speed. Instead of that, you start building a different type of machine. Now, I have drawn over here a chart. At Los Alamos, they had a chart coming out, we'll say, to here. They took the fastest machine they had at any one time and fitted a curve, and they got this curve, e to 22, 1 minus e to t over 20, with 1946 being times 0. Well, I had one of these charts. It was back of my desk, and we'll say 15 years later, at Bell Labs, it comes out. I glue another piece of paper to that one, extend using that formula, the curve out here, and I look at the latest fifth generation Japanese machine, practically on the curve. So I say, you know, that's really not a bad machine. And it predicts a saturation of 3.5 times 10 to the 9th operations per second is what you're going to get for a one processor machine. It's experimental. It's no theory at all, except it's based on the words I told you: the size of the molecule, the velocity of light, and heat dissipation. That's what you expect out of one processor. Now let's come down to the von Neumann machine. The first electronic machine was, well, sorry, I got to go around. I first got to talk to you about how I got things going in Bell Labs. I didn't want to argue with my boss. He was a nice guy. Furthermore, I knew the principle which I commend to you very highly. Never, never let your boss say no. Once he says no, almost no bosses have got the guts to say, yes, I was wrong. So I never asked him for a machine. I simply rented machine time outside, and I ran up a big bill. I rented machines in IBM, I rented Univacs, I rented whatever was available any place I could to get jobs done. And he couldn't complain about it because he was not paying it. The group I was doing the computing for paid the bill. But he could see. So he says to me one day, you know, Hamming, it might be cheaper if you had a machine on here instead of having to go around all the time. I said, yes, it would probably be cheaper. He said, which one do you want? I knew what I wanted. I told him, bingo, I got it. I didn't let him say, no, you can't have a machine. And I commend you always, never ask a question if the answer is likely to be no, unless you want no for the answer. I had one boss, and only one, who could rise to the occasion and said they changed their mind. And that was John Pierce. You may have heard of him as a really famous scientist. He was my boss for a while. He was an impossible boss in the sense that he was interested in science. He never fielded forms. He didn't do this, that, and the other thing. But you went to John and said something. He'd say, no. And I said, but John, what about so-and-so? John would say, you're right, I was wrong. Go ahead. He's the only boss I ever had who could do that. And I'll bet you have not had many bosses who could do that. So don't let them say no. Never let a boss say no if you can avoid it. Now, in credit to my boss, besides being against him, he was also a big help. He made me realize the problem was not to get the most number of operations done per second, which is the first thing I thought to do. I got a computing center. How many numbers can I calculate today? He got me to understand that in some sense it was the number of micro Nobel Prizes. How much useful computing could I do? How much important computing could I do? That changed a great deal of how I went about things, and I came up with a motto which I commend to you. The purpose of computing is insight, not numbers. We are not computing numbers just to get the numbers, although sometimes we have to get design factors. Mainly, we must have understanding, because if we don't get this understanding, we will be cut off at that technological level forever. Understanding is what will enable us to go further and further and further in understanding and making progress. Now, this motto, the purpose of computing is insight, not numbers, was modified by my friend at Stanford. He said the purpose of computing numbers is not yet in sight, which is also true. Now, it's necessary to talk about details of computers because I'm working to some other topics. The basic parts are two-state devices. Two-state because of our ability to do technology. We are unable to build fast, reliable 3, 4, 5, and 6-state devices, although we tried. we tried to build some Decatron 10-state vacuum tubes. Yeah, we could build them. We couldn't make them work reliably and fast. Our technology dictates a binary system because of the way it is. That means that our two-state devices are either conducting or not conducting, or either they've stored something on a charge or they have not. And they either gate something or they don't gate something. Or if two pulses come in, they put one out. If only one comes in, they don't put it out. Very simple two-state devices. These are put together into larger arrays like registers of, say, an array of 64 bits. But they're only that. Now we put them further into arithmetic units to add, subtract, multiply, and divide, or logical control. But they are parts of these little bits. That's all they are. Now going to still larger devices, we built a storage device, arithmetic units, and such other things. And we built a machine which works about as follows. Oh, by the way, I didn't draw. This is a part here. And you see this part is this. That part is the caveman days and so on, when progress in computing was very, very slow for a long while. Exponential tail out here. Then there's this rapid rise. And here's that saturation, which is really this. I talked about this yesterday. The machine we built are as following. There is a current address register. Somewhere in the machine there's a register. The machine goes to that current register and finds an address. It goes to the storage and gets that instruction. It takes that instruction, decodes it, and executes the instruction. Then it takes one and adds it to the current address register. Then it goes back. It reads the address. The machine does not know where it's been, does not know where it's going. It does bing, 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 bing. Now, some instructions here will put a different number in the CAR and not add one. Those are your branch instructions. But outside that, the machine, bing, 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 and this or the branch instruction. Build out of binary parts. There is no meaning to those bits. The machine either puts the two bits through or doesn't. It doesn't know any meaning. We are the people who put the meaning into the bits. There is no meaning inside. Two bits go up here, the machine gates it. One bit doesn't. It doesn't know any meaning. And around this thing here, you can see that it doesn't know where it came from. It looks at the current address register. It does not know where it was before, whether it was one previous or whether something was substituted in there. It has no larger picture. None whatsoever. Now, I'm reviewing this because I want you to be clear what machines can and cannot do. They are machines in the classical sense of a machine. And before I leave the topic too far, I want to remind you that Democritus in 460 BC, something like that, maybe they don't really know when he lived, said, all is atoms and void. There is nothing else. And if you throw in the word radiation, this is basically the view that physicists take. The world is composed of molecules and radiant energy, and there's nothing in between. Well, are you atoms and void? Is that all there is to you? This problem is going to come up. Are you merely atoms and void? One molecule bang against the other, bang against another, and so on, and this is what happens? Or is there more? Now, if there is more, if you think there's a soul or something, the question arises, how does that soul affect the motions of the molecules of your body? How does thinking affect the motion of molecules? Are you a machine like this is a machine? Or are you more than a machine? If so, in what sense? What can you prove and what can't you? Because on this difference, if there is one or not, depends upon how you're going to try and use machines. If you think there is no difference between you and a machine, it is probable that you'll do one thing. If you think there are significant differences, you'll do something else. If you think machines can do very, very little, you will not be a leader in thinking that and progressing on the use of computers. On the other hand, if you think machines can do anything humans can do, I will promise you, sometime or other, you'll fall flat in your face. Somewhere between these two, that you are only a machine and machines can do anything you could do, which is the hard AI attitude, and the other view that there is some something more to you. There is self-awareness, self-consciousness. Maybe you want a soul, or various other things. Incidentally, souls are very difficult things. Somewhere in the Middle Ages, wanting to know when a person died and how much a soul weighed, they put a guy on a balance and watched him die, and there was no sudden change in weight. But they were sure the soul was gone, so they concluded if you have a soul, it doesn't weigh anything. It's something else. It's a hard problem. It causes trouble all the way around, and you are not going to get out of it. I say again, the fundamental problem you will face in the use of computers is, here is a mechanical thing. It does that sequence of things pretty much in the classical von Neumann machine, and it just does what it does. Molecule bang against molecule. If the two currents are there, it gates it. If they're not, it doesn't. If these two happen, it does. If it doesn't, it doesn't. It operates on bits. Every throughout the machine, each piece operates on a bit. It doesn't know what it's doing. It doesn't know anything. It goes through this cycle endlessly. That's all there is. Are you that, or are you more? How would you prove one or the other? The mere assertion won't do any good, because I can get a machine to print out, I've got a soul. You won't believe it. I have a machine print out, I am self-aware, or I am self-conscious. You won't believe it. Why should I believe you when you say you're self-aware and self-consciousness? That's the problem you face. You are trying to work with machines, and you must get a firm grasp on what machines can and cannot do so you can work with them. The attitude I had throughout all my career was, and I had a lot of trouble with my bosses, I am not interested in the competition of man versus machine. I told them again and again, I said, I am interested solely in what man and machine can do together. And that's still to this day, after 40-odd years, I have stuck with that attitude. What can man and machine together do that we want done? Not can I substitute man for machines, although there are sometimes I do. I told you the other day, the most impressive thing I think about a machine is its freedom from boredom. It's very impressive. You can't put a human being watching something for 3 years, and when suddenly the blip occurs on the screen, expect them to react. I can put a machine on a job, when a blip occurs, the machine reacts. I can have machines monitor long-term safety risks with success. I can't put humans on a job. Humans are very bad things in many ways, and I listed them all at the end of the first chapter, I believe, and I'll come back to them periodically, all the defects. You're well aware of some of the advantages. You have got to get those clear in your head, and I want to, when I go on about 3 or 4 more lectures from now on artificial intelligence, I will say repeatedly, it is not my business what you believe. My business is that you get it clear in your head what you think, and also be able to express it clearly. We have an admiral coming in, nice lady. If you are asked, can machines think or not, by her, I expect you to answer. It is not my business what you answer. My business is that you answer coherently and clearly. You see my position in this education business? It's up to you to get your thoughts clear. Quoting me is not legitimate. In fact, in a discussion, I will always take the opposite side, to compel you to think of what you believe. You are responsible for your beliefs. I am not responsible for your beliefs. I am responsible for making you think, but not what you could think. I'm particularly poorly placed at that. I am so lost in the past that I have difficulty grasping the present, let alone the future. After all, we calculate atomic bomb designs in 1 operation per second. That could be done now on a machine in about 2 seconds. We worked around the clock for 2 or 3 months to get one answer. I'm not really adjusted in many ways to the speed of modern machines. I tend to think of the cute tricks we use to save milliseconds and microseconds. It doesn't do much good now to save microseconds. You have to save 1 million of them to save 1 second. It isn't a paying game. It was in my youth when we had slower machines and we didn't do such large things. Now it doesn't. So I'm really not oriented well to guide you in the future. I can merely tell you the past isn't too good a guide in the future, and you must make up your mind of your relation to machines, because machines are going to be all over the world. There's going to be increasing numbers. So I see you next Tuesday, right?